So here is the new oscillator, and here is the previous one, which is not quite as good. It has plus 18 dBm output power and a similar noise floor as this one, maybe a little lower. Anyway, both of them are powerful enough for this box, which is a frequency mixer. It's from Mini Circus, a 23 dBm level. So I have to attenuate. There is a 6 dB attenuator on the 1 watt signal source, so I give 24 dBm. This is a low pass filter. The 18 is attenuated by 3 dB, and then there is a low pass filter into the mixer. And now the mixer is routed through this low pass filter. It's a dual low pass filter, I'm just using one of them. And then into this sound card. It's an UADC4, it's a prototype for that. And also directly from here into the oscilloscope. And here you can see the level I have, and I adjust the manual gain setting for this signal to precisely fill the screen. Like this. Now I have the level of the signal. And the sound card here is AC coupled, and the frequency is too low, so I don't get the full amplitude into the sound card. I have connected this signal generator to this connection point, so I send it into the sound card as well as into the oscilloscope while the mixer is disconnected. And I have set the level to be the same as I saw on the low frequency resulting in the mixing of the two oscillators. And then here I can set the calibration of the INRAD to make this level that I observe a 0 point, 10.65. So I feed 10.65 here, and now I read 0 for a signal that has the same level as the mixing product between the two oscillators. The filter bandwidth is 100 Hz, and that means I can read now the noise floor in a 100 Hz bandwidth, and that is minus 131, which means minus 161 dBc per Hertz. And I disconnect the oscillators by disconnecting here. And there is no change in the noise floor. It means the noise I see comes from the sound card, not from the oscillators. And that's it at the separation of 2.5 kilohertz. If I go closer, like here, there is some more noise from the sound card, as you can see, but not so much. And I connect back the mixer. And then it's clear. I don't see any noise from the mixer output. And this is 900 Hertz from the signal frequency. So I go a little bit closer than this. Here is 250 Hertz from the carrier, and there are many overtones of this low frequency here, and there are some spurs that I don't know from where they come, but it seems the noise floor is elevated. I moved to 500 Hertz from the signal frequency, and I wait for a while and then remove the signal to see how that affects the noise floor. And I look at the noise floor in the here, and it doesn't change. So what I see is limited by the sound card at 500 Hertz and above. I have added a transformer to step up the voltage a bit, and a capacitor in series to not saturate the iron with the lowest frequency. Then I have added this directional coupler so I can monitor what I'm sending into the mixer. It's on the mixer, and then there is the directional coupler, and of course the low pass filter. Then I added an attenuator and a hybrid here, so I can send two different signals at the same time into the mixer, or one or the other. At the moment I'm sending two equal signals into the mixer, and I have set the attenuator on, I don't think you can see that, 20 decibels. 20 and nothing here. And then calibrated the S meter to show -20. And this is what I see from the directional coupler. It says -29.7, means the signals are about -9.5 dBm. I cannot send both of them at the full amplitude at the same time, because that's far too much for the mixer. But I can step up by 10 dB without any serious problems, I think. Well, it went from -20 to -10, so that's okay. And if I go for the full level, it looks rather ugly and I get problems here. So I have to switch off one of the signals. Sorry, I switch off the signal close to 0, and this is my calibration signal. It should now show 0. Actually it shows -0.5 dB, so there might be 0.5 dB of compression here. Now I don't worry about 0.5 dB at this time. So it is calibrated for a signal 2.5 kilohertz away from the from these oscillators I want to measure. So I switch off the signal generator and switch on the test object. And something is not right. Or maybe, well, I will look at this. I removed the attenuator and changed a couple of cables, and now it's okay again. And when I read the noise floor here, oops, I see -124, and the bandwidth is 100 Hertz. So that is 144 dBc per hertz. And when I switch off the signal, like this, the noise level is the same. It is still, well, maybe it changed a little. Minus 124, and here we have minus 124, so it's the same. This is still sound card noise only. As it turns out, this transformer had a far too high transformation ratio, so I use only half the secondary, and that gives a little bit more signal, and I have recalibrated it now to show 0 on the signal level of the signals I have. Now both signals are present, and I switch away the other one. Oops. And then I want to look at the noise floor again. And it's maybe a little better. Minus 126. And looking at it up here, well, too much white areas, so I don't see much on the camera. I cannot control this thing very well. Well, maybe, yes, here I can see. Now I switch off, I disconnect the mixer. And here there is no change. And looking at the noise floor, it looks very much the same. So minus 126 in 100 hertz. That's minus 146 dBc per hertz at a separation of 2.5 kilohertz. And still it's the properties of the sound card I'm looking at. I don't see the oscillator noise yet. I have now this arrangement. The high power local oscillator. It's split with the hybrid to 2 equal and 3 dB weaker signals. One is going directly to a mixer, that's 23 dBm mixers, and the other through a 90-degree delay line, a quarter wave, to another identical mixer. They then receive 27 dBm each, and that's within the specification. The lower power local oscillator plus 18 dBm, there is a coupler, so I can send a signal into the system to check calibration at an offset frequency. Then there is a low pass filter at 13 megahertz, because sending overtones into the mixers is going to be a bad idea. That generates false frequencies. Then there is a 20 dB coupler and a spectrum analyzer, so I can measure what I'm sending into the mixers. And a hybrid splitter to split those 18 dBm into two 15 dBm signals, which are well within what the mixers can handle. And after the mixers, there are low-pass filters, and then a transformer to step from 50 to 300 ohms, because the input impedance of the UADC4 is 300 ohms when it is set for maximum gain. And of course the same in both channels. And here is what I'm sending into the mixers. It is -5, and then there is the +20, so this is +15 dBm. And this is what I see on the S-meter graph. I can read it out. -132.1. And now I disconnect the signals into the low-pass filter here and put 50 ohm dummy loads. And I can clearly see that the noise floor is lower now. It means I do see sideband noise from the oscillators, or maybe from the mixers or something else, attenuators or whatever. Anyway, what I see here is -133.45. I switch on this signal generator, and I have set it to a level -25 dBm here. That is 20 decibels below the LO that I'm testing, the +18 dBm LO. And I want to read now -20 here. And indeed, that's what I do. -20 dBm. What I have now is a proper direct conversion radio. This is the signal, this is the mirror image, and it's suppressed by far more than necessary to do proper evaluations of noise sidebands and such things. And you can see the sideband noise of the Hewlett-Packard is fairly visible. So I switch it off, and then I start the local oscillator again, that unit that I'm testing. And of course it adds very little to the noise floor. So here is what I found. The noise floor and the noise floor plus the sideband noise. Noise increment due to the sideband noise is 1.35 dB. That is 1.365 times. The sideband noise is then 0.365 times the noise floor. And that's minus 4.4 dB. So what I found is the sideband noise is minus 157.9 dBc per hertz at 2.5 kilohertz. And this is the sum of all sources of sideband noise, the two oscillators and anything else that might generate sideband noise. Probably connectors, attenuators and other stuff are significantly better than this, so I think this is the sideband noise of the 18 dBm local oscillator, because I expect the other one to be significantly better. I have moved to an offset frequency of 500 Hz, and the level is the same, and I expect the calibration to stay the same, and it seems to not have changed. It's still minus 20 dB here. 19.97. That's accurate enough. So I switch this off and switch on the test object. And here is the noise floor. minus 127.11. It's significantly higher at this close range. Now I've placed dummy loads instead of the cables from the mixers, but I keep ground loops the same by having the connectors screens connected to the box. And the new noise floor I see is here, minus 130.39. So here are numbers at 500 Hertz, the noise floor and the noise floor plus the sideband noise, and the noise increment, it's a factor of 2 and a little bit more, so sideband noise is stronger than the system noise here. It's half a dB above the noise floor of the system, and that means that the sideband noise is minus 149.9 dBc per Hertz at 500 Hertz. Going from 500 Hertz to 2.5 kilohertz, that's 5 times, that's 7 dB. And what I observe is a difference of 8 dB. That's close enough, so it means I am in the 1 over F region. That means that at 50 kilohertz, if that is still within the 1 over F region, I should expect minus 171 dBc per Hertz. And that is, of course, then the lower power oscillator. I don't remember what I got when measuring it with the notch filters, so I will check that. I'm now looking at this oscillator through the notch filter. The signal level I see is minus 4 dBm, means plus 16 dBm. And the noise level is much higher than expected. Something is wrong here. I see the noise at something like 3.5 dB. I will connect to the noise head and see what is the equivalent noise temperature. I've set the noise figure meter to its maximum, 17.5 dB noise figure. You can see the high range and 17.5. But that's not enough. The noise is, what is it? 2.5 dB below what I saw as a sideband noise. So the noise is corresponding to something like 20 dB. That means 16 dB dBm power plus 174, that is 190, but minus 20 for the noise figure. That means minus 170 dBc per Hertz. That's quite similar to what I found with the mixers. Now, what is the problem? I have written maximum 18 volts on the unit, but it seems I have given it a little bit more. I will turn down the voltage while looking at the screen here. Now it's 17.5. There is still some kind of instability. So this unit isn't quite stable. I don't know why. Maybe it depends on the load it is looking into. Now the level is just a little higher, still about plus 16 dBm. And the voltage is a little bit below 18 volts, 17.5. And the noise is much lower. It's at this level now. To get a similar noise level here and here, I have to set the noise head to a noise figure of 5 dB or slightly less, and it's now on the low range, as you can see. So it's about 15 decibels. So it's about 15 decibels better now, and I will connect back to the sound card method of evaluation at close range. I now see minus 126.48 with the signal present. With the 50 ohm dummy loads replacing the mixer, the level I see is minus 129.9. And this is not what I expected. I'm now feeding the oscillators from separate power supplies, so I can set the voltage below 18 for the one that requires that, while the other one wants something like 22 volts. What I see on the Linrad screen, it's not very encouraging. The noise floor is at minus 125.8. With dummy loads here on the low pass filter input, rather than the mixer, the noise floor is minus 129.88. I'm now using all 4 channels of the UADC4. It's the same signal on this pair as well as on that. So 2 RF channels is what Linrad will see. And the signals I send into it, the same as before. The strongest one here, it says minus 3.4, and the other one is minus 23.6. So it's 20 dB lower. The frequency is 2.5 kilohertz above 10 megahertz. And I have clicked on the signal, put it at the center of a 100 hertz passband, and I have put the calibration for this signal to read minus 20, well, minus 20.6. I don't take the decimals so carefully now. You can see here I have enabled the correlation spectrum, but the correlation spectrum and which is yellow and also green, but you don't need that at the moment. I can press Alt Z to restart the green, and you can see that the green is just a little bit below the white here, because at the end of the spectrum the noise from the sound card dominates, but near the carrier all curves are at the same position, because this is noise, sideband noise from the generator, and the sound card does not contribute. So the noise is perfectly correlated between the two channels. Now I switch off this generator. So it's only the two 10 megahertz signals, and I clear the correlation spectrum. And it takes some time for the averaging to take place, and it's clear that the green spectrum is well below the yellow, and the green is now from 200 350 averages, and I will wait for a while. I have had some stability problems with this box. It misbehaves if the voltage is too high or too low, and the range where it is okay is very narrow and depends on the temperature, so that's very impractical. I have made some adjustments to it. Now the power I see here is minus 1.5 dBm, means 18.5 dBm into the receive system I'm using. I have set this generator at 500 Hz offset, and the level minus 31.5 dBm, so that means 30 dB below. And I calibrate Linrad now to show minus 30, minus 29.97. And I switched off the Hewlett-Packard signal generator and switched on the crystal oscillator, this one. And then I look at what is the noise level I can see. You can see here the frequency is drifting. The difference between that local oscillator and the other oscillator, that one, is changing as temperature changes. It does depend on the voltage slightly, so I can adjust the voltage to make the frequency difference very small. And then it doesn't go through the coupling capacitors of the audio system. I do have some contribution from 100 Hz. I don't know why. I think I didn't have that some time ago. Yeah. Now it's not there in the green channel, not much. But it is in the orthogonal, but that doesn't matter. I press Alt-Z. And the noise I see here is minus 130.4, and the correlation is about 2 dB below. So most of the noise I see here comes from that receive system. And now I see something is going wrong. I have to look for that. Stop this. Well, I had induced some grounding problem. I have to connect to ground here. And I will check more carefully the groundings. At the separation of 500 Hz, I see minus 132.3 on the S meter, and the correlation indicator shows me that correlation spectrum is 1 dB below, or 0.7 or something. So the sound card does not contribute significantly at this close range. I am now 2.5 kHz above with the same signal level. Sensitivity is a little bit different because I have the transformers in the path. So I had to change this calibration by half a dB, but now it reads minus 30, as it should. At 2.5 kHz, the S meter reads minus 139.1. And the track is a little bit more noisy. It means there is some kind of abnormal noise modulation on something. Correlation is 2.5 dB. Generator is now 10 kHz up, and I look at the S meter and it turns out that the calibration is the same as at 2.5 kHz. The transformers here are flat, and also the sound card. The S meter reads minus 142.6. That is the white curve you can see here, but correlation is 5.8 dB below. That's the green curve here. At 20 kHz I see 144.1 with 12 dB of correlation. Now 30 kHz up, I had to change the calibration by a couple of tenths of a dB to read still minus 30. And at 30 kHz the S meter shows 142.6 and correlation is 12.3. With dummy loads at the input of the low-pass filter and into the sound card gives a situation like this, and I'm still 30 kHz up, and the S meter shows minus 143.4 and correlation is minus 14. And at 20 kHz the S meter shows 144.9 and correlation is very close to 14. And you can see the correlation is very similar over the frequency range. A little bit smaller here, I think. At 10 kHz, 145.6 with 13.5 dB on the correlation. I did connect the mixers and verify calibration because I have changed it a little with frequency. So now it is correct again for this frequency, and the noise floor I see is minus 145.4 and with 13.1 dB of correlation, or maybe 13. And now finally I am at 500 Hz. The baseband looks like this. These are overtones of the mains frequency coming into one or the other of the oscillators probably. The S meter gives minus 141.9 and correlation is about 10 dB, minus 10. So here is what I found. At 500 Hz offset, the S meter and then the correlation that shows how far deeper down the signal that is identical in the two channels is. And it's only 0.8 dB because this close to the carrier, the sideband noise of the oscillators dominates strongly. And with the dummy load I get a much lower level, and correlated noise is much lower also, which means that the noise I see from the sideband of the oscillator is minus 153, while the noise floor with dummy loads is minus 172 almost. Now at larger frequency separations, the difference between the oscillator and the dummy load is small. And this table is the differences, goes from 18 dB down to about 3 dB. And the final result I can compute from this is that the noise level, the sideband noise level, goes from 153 at 500 Hz down to almost 180 at 20 and 30 kilohertz. And probably this is the noise of the not black painted oscillator, the older one I have. And I think this is consistent with what I found with the notch filters, but it's a long time ago, I have forgotten. But it should be significantly worse than the latest oscillator anyway. So this should be what I'm looking at. And here maybe the sound card noise contributes a little bit more than I have evaluated. It's always difficult when the system noise is similar to the noise of the test object. Just looking at the screen here is quite clear. We can see that the oscillator noise dominates in this range. And here, when the noise goes up, it is probably the sound card that dominates. So a good measurement on the LO should be here. And at this time I see a correlation of 13. It's from 6,000 averages, so it should be fairly reliable. And it's also clear that the correlation noise forms a nice straight line when it's produced by the sideband noise, but it has structures when it comes from the sound card. It comes from digital things that are synchronized somehow with the sampling rate. And at this time I am at 20 kilohertz. I see 144.2 and then 13.5.